We actually had this lecture planned back in 2020, right as COVID was hitting the streets. So it's been a long time coming, but I really appreciate you being able to speak tonight. So our guest speaker, in case you're in the wrong place, is Dr. Dylan Fischer. He's a scientist and faculty member at the Evergreen State College. And Dylan, would you mind introducing yourself further?
Yeah, that's great. Thank you so much for having me. I'm really honored to get to present to everybody here, and hopefully voice and sound and image are coming through all right. I've been at Evergreen since 2005. I started there as a faculty member, and I've been teaching forest ecology there. Mostly it's kind of hands-on practical forest ecology work there. My background in forest ecology goes all the way back to before I was an undergrad at Oregon State University. I did a lot of work in the Southwest around Flagstaff. I got my graduate degrees in Northern Arizona University, working in ponderosa pine, kind of frequent fire systems and cottonwood riparian forests throughout the Intermountain West, and then transferred back took the job at Evergreen here, coming back to the Northwest in 2005. And since that time, I've expanded and kind of have do research in a variety of temperate forest systems and all over the Mountain West, including Mount St. Helens behind me, and other locations throughout the West. So this talk is really going to be kind of a summing up of some carbon concepts and scenarios related to our forests that are just right here in Olympia, and some projects that I've been working on now for over 15 years. So Michelle, if that's enough for you, then we'll go ahead and move on, and I'll go ahead and start a slideshow. I think that works. So great. And I'm going to go ahead and transfer to a PowerPoint here. If you can just give me a thumbs up and let me know that that's coming through for you, that you can see a title slide. Some pretty pictures along the top. Yeah, high five. I think that means thumbs up. So
it works.
Okay, great. Okay, we'll continue on then from there. All right. Okay, well, this talk is a distillation of a bunch of stuff that I've been working on for a number of years, like I said before. This is going to be about forest carbon in the Northwest and some kind of big concepts related to it. But I thought I'd start big for this talk. And so let's just start with a map of US forests. And the US have a lot of forests, maybe not as much as some of us imagine. We tend to imagine ourselves as a forested country. We're just looking at the lower 48 here. Of course, Hawaii and Alaska would add to this. But in the lower 48, we got about 40% of our land base, or 50% of our land base. Somewhere about half of our land base is forest, sometimes more, sometimes less. And you'll notice, we occupy a really special position here in the Pacific Northwest because, of course, west of the Cascades, we are known for our dense forests. Let's take another view, though. This is a map that is looking at carbon density. And so what carbon density is it's the amount of carbon that you have per unit area, in this case per hectare. And so this is megagrams per hectare, and a megagram is a ton. And so we're looking at a metric ton per hectare, which is about 2.5, somewhere in the neighborhood of 2.5 acres. So you'll notice something else that's really unique about the Northwest in this image, which is that we have the highest carbon density in the country. And so if you want high carbon dense forests, we are the place to go, which is no surprise to many of us. We love our forests for their size and their immensity, their density. We know them to be places where there's a lot of vegetative mass, and about 50% of that is carbon. We might think of this as a green and padded realm. It's a place where the forests are so dense that light barely penetrates to the floor in some cases. And there's so much vegetation, it's all busy photosynthesizing, and it's all busy pulling carbon dioxide out of the air almost all the time. Things that make our forest unique on a nationwide basis really has a lot to do with our high rainfall amounts. We're a temperate rainforest largely west of the Cascade crest, not everywhere, but in many of our forested systems. We are known for our big trees. These trees tend to also decay very slowly. I've traveled all around the world looking at temperate rainforest systems in different locations. And one thing that's really unique to me about our forests is that our large woody debris and our trees don't tend to decay on the ground as fast as they do in other systems. We have really high carbon density, not just the highest in the country, but actually that's some of the highest in the world. And so you have to go to other temperate rainforest systems in Tasmania or Patagonia to find similar carbon densities. And of course, the large trees and older forests that our region is known for have really defined a lot of our public policy and environmental policy debates. And at the time that I was an undergraduate student, the spotted owl issues were really heavy. And this dominated a lot of how we thought about what we were going to do with forests in terms of conservation and how we were going to think about them. And today I'd argue that the forest role in the carbon cycle is really kind of taking a similar stage, because we have these big trees, we have these intense carbon dense forests, and we've lost a fair amount of that due to deforestation in the past. And there's some public debate about how we treat our forests going into the future and what kind of role that's going to play in terms of how our forests interface with global climate change. Well, when we think about carbon and forest carbon, it's really important that we address some nuance. And this is because how forests deal with carbon and how carbon moves through forests depends on the time scale. And so it's best to think about forest carbon in terms of both pools of carbon and fluxes of carbon. So we have large amounts of carbon that are on the landscape at any one time. And at any one time, we also have carbon that's moving into that system and carbon that's moving out of that system. So carbon's moving into that system like, and through the system like the hikers here in this photo, or carbon may be dissolved in the stream water in this photo, but it's also moving in through photosynthesis. So the plants are taking up carbon out of the atmosphere, and it's moving out through decomposition. So decomposition of the dead material that you see on the forest floor here is going to release carbon back into the atmosphere. So pools and fluxes. This is maybe better illustrated by, well, definitely probably better illustrated by this nice cartoon here that is showing you how carbon dioxide, the white dots here, are taken up by trees at the center of the image, converted to sugars and plant biomass. They turn into green dots, and they're maybe moved down below the tree into the root system. Maybe they're given to some mycorrhizae, maybe some soil-borne organisms eat some roots or mycorrhizae, and then they embody some of that carbon. And then eventually respiration releases that carbon dioxide back up into the atmosphere. So forests are a pool. The sage-colored forest in the background is a pool of carbon, and then we always have fluxes coming into and out of the system. When we think about this in more of a static diagram, it might look something like this. So I'm going to show a series of images here that come from the U.S. Forest Service. Here's one where CO2 is being taken up by trees on the right side here. As those trees grow larger, there's more carbon stored in those forests. And then, of course, fires and disturbance events can release that CO2 back into the atmosphere. Additionally, burning of biomass or using wood products can result in waste products that decompose, or a change to forest conditions that result in release of carbon back up into the atmosphere. So there can be a cycle there. Another way to view this might be thinking of a natural forest alone without any human impacts. And so we can think about carbon uptake, storage, and growth. We can think about an older forest that has a lot of carbon. Maybe it interfaces with a fire or some type of disturbance, which removes some of the carbon, but not all. And so carbon dioxide dips. And then as that forest regrows, we get an accumulation of carbon again in a store of carbon, in a pool of carbon in the ecosystem. One analogy that forest carbon scientists have used for a really long time is the analogy of a bathtub. And so in this cartoon image, the water in the bathtub would represent the pool of carbon in a system. And of course, carbon is coming into the system through photosynthesis, that's the dripping faucet, and carbon might also be leaving the system, both through natural disturbances, which are represented by the drain, and in this case, there's a leaky towel hanging over the side of the tub that would represent losses due to forest harvesting. This comes from the National Forest Service, and of course, the Forest Service has not been doing much harvesting in recent years, and so that's a relatively small impact on those forest lands these days. Here's an image from a global analysis that kind of puts some of this together. And so this is actually coming from two separate papers, one Pan et al. And another Bacchini et al. And both of these papers tried to look at carbon on a global scale in forests, both in terms of rates of uptake and rates of release. So we can think about these fluxes in terms of uptake and emissions. And in the first two bars from Pan et al., the dark blue and the light blue bars, the emissions are, the uptake is represented by the blue bars, and the emissions are represented by the dark blue bars. And so gross deforestation emissions are the dark blue numbers. And then the medium blue bars represent the net of both of those influences. And so the net rate of emission on a global scale is positive, meaning that our forest management approaches are resulting in increases in CO2 to the atmosphere in that analysis. A similar analysis by Bacchini et al. Is breaking this down by what components are contributed by industrial logging or fuel wood harvest, or things like afforestation, places where forests are planted where they weren't previously. In the image behind me at Mount St. Helens, we have forests that are regrowing in a location that over 40 years ago was devastated by the eruption of Mount St. Helens. And so that's a net carbon sink. If we put this together on a global scale, though, the situation is much more geographically complex. And so on this map by Harris et al. From 2021, we have a global map of forest fluxes. And where you see pink, those are sources of carbon to the atmosphere. So those are places where we have deforestation events. In southern Brazil, we have places where we've had tremendous fires, many of you may have heard about in recent years. In Malaysia, we have widespread fires and logging that is resulting in a lot of loss of forest carbon. And then we have other areas where we have sinks of carbon, and you'll notice a dark green patch up in the Pacific Northwest representing a sink of carbon. You'll notice areas throughout Europe and East Asia where we also have strong sinks. Southern Patagonia, southern Chile, also strong sinks for carbon in those forests. Same with Tasmania in Australia, which we'll come back to at the very end of the talk. Well, getting a little bit more local, here's Thurston County. And instead of looking at fluxes, let's start with pools. And so here we're looking at the amount of forest in our county and surrounding environments. Darker green means more forest. And then we've got some statistics up there about the amount of both forest and the amount of carbon that we have in our local forests. And you'll notice that we have some denser patches of carbon around Olympia and some lighter patches. A lot of this can be measured these days from satellites. And so we're getting increasingly better resolution on our remote sensing, in our remote sensing tools that are allowing us to document this kind of thing from space or from aerial imagery. And so you're going to see a lot of that. I'm going to go through a bunch of examples of that here in the talk. Well, here's an example where we can also, not only can we look at the pools of carbon based on absorption of light, but we can actually look at photosynthesis rates. So in this case, this is looking at the flux of carbon into forest ecosystems in Oregon and Washington here. From 2008, this is just, I could pick any month or any year. I just happen to have this slide already. And so you can see the darker green areas where in July of 2008, more carbon was being taken up, more photosynthesis was taking place in those darker green areas around the Olympic Peninsula and right around where we call home in Olympia. So in Thurston County, in 2010, we had close to about 120,000 hectares of natural forest. It's about 73% of our area. In 2021 alone, we lost about 1.26, 1.25 thousand hectares of natural forest. And that's around the equivalent of about 1 million tons of carbon. So that's actually a lot of emissions. And some of that forest is natural forest, some of it's in plantations, and then of course some of our land base is not forest at all. But the good news is that forests don't, when you cut forest, you're not just emitting carbon, forests regrow, and we have forests that are very active in taking up carbon dioxide. So we have pools, and then we have fluxes, and loss of forest and the resulting emissions from that are just one of those fluxes. It turns out in our county, if we look at the balance of carbon released and carbon absorbed, we find that we actually have a net positive, or a net, in this case, negative, meaning it's sucked out of the atmosphere into vegetation, uptake of carbon. So we have more removals of carbon than we do have emissions of carbon into the atmosphere in our county, which is a pretty neat thing. Well, I want to transition here a little bit into some direct research that I've been doing with students at the Evergreen State College since 2006. So here in the foreground is our college, surrounded by 1,000 acres of forest, around 300 hectares of forest. And these forests vary in age from somewhere close to 80 years all the way up to over 150 years old. So we have some legacy forest on campus. They're diverse stands. And in 2006, we decided to implement a structure for repeatedly measuring these forests to measure specifically carbon and to watch that change through time. So this is a map of our campus and the surrounding forest in green. And where you see a letter and a number, those are plots, permanent plots, circular plots where we go to every 2 years. And every 2 years we go in and measure the forest in those locations. We'll measure every tree, every snag, every down piece of wood. We'll measure soils. We'll measure carbon flux, and we rotate through that. So just about every 2 years, we're doing that again. Right now. And so we have about 44 of these locations. And from time to time, we'll also do repeat photography. So I'll show you some photographs of these plots so you get a sense for what this forest looks like. My guess is this is going to look a lot like the state forest that you may have been to in Capitol Forest or in state parks in our region. So here's one of our plots that is largely deciduous dominated, a lot of sword fern in the understory. Here's one of our nice plots that has a legacy stump, probably from the first logging event in the 1800s on our campus, complete with springboard notches indicating how it was logged. This is an old Douglas fir. It gives you a sense for how much the forest has changed in terms of tree sizes. This is a forest that's starting to close in with a dense cedar canopy. We've got some deciduous trees that are being shaded out. You can see the tags really clearly in this photo. Those tags are where we measure the trees. And here's another plot that has had a big opening in its canopy where it's expanding and getting more light in and fewer trees over time, even though the remaining trees are larger. In each of these plots, we have every tree tagged and we keep it in a database, and then we return every 2 years and remeasure the diameter. And there's a long history of this in forestry. Measuring that diameter with a diameter tape allows us to make all sorts of predictions about just the structure of the forest, but also the amount of carbon in it. And we'll talk about that. These techniques are common all around the world, which is kind of cool. So carbon scientists collaborate a lot on methods, and we have a pretty standard methodology these days for how to do what we call biometric estimation of carbon, which basically is just a fancy term for saying we go and we measure how big around the tree is. And it's not rocket science, folks. A bigger tree weighs more and has more carbon in it. I mean, that's really what it's going to come down to. So we use that diameter measurement as a way of measuring the size of the tree, and then we're going to correlate that with the amount of carbon, and it's a very tight correlation. We're fortunate to have some pretty good predictive ability there. We've been doing this work at Evergreen for a long time. This is a picture from 2005, actually at Mount Rainier National Park, where we were using similar methods to measure carbon in forests outside of campgrounds. This is near Cougar Rock Campground, which some of you may have been to. Well, what do we do with these data? What we'll do is we'll take the size of a tree. So let's start on the left with that little tree there, and we go and we measure the size of that. And it turns out that the tree carbon content is proportional to the size of the tree, and the size of the tree can be really nicely measured by a single diameter measurement at the base of the tree. And so again, this isn't rocket science. We're just saying a larger tree weighs more. And we're fortunate that we have some really nice equations predicting this. And they tend to have, their own coefficients and that sort of thing, but these tend to be really strong relationships. And we can estimate about 50% of the biomass of those trees is carbon. And then if we come back at time 2 and we've measured at time 1, we can take the difference between those divided by the time that's passed, and we have an estimate of how fast those forests or those individual trees are accumulating carbon. And so we can do that in any patch of ground that we go and measure, and we can determine both the pool and the flux, the net flux over time. So our data sets at Evergreen actually go back to 1977, which is kind of cool. Some of the first forestry programs at Evergreen started measuring this in a series of plots in 1977 that were recovered in 1987, lost, then recovered again in 1997, lost, and then recovered and found and remeasured again by my classes and me since 2008 here. And so what you can see from this graph is it's showing you the tons of carbon per hectare. So our carbon density, how much carbon we have per land through time. And what you should notice is a steady increase as we go from 1977 to 2008. This analysis had to be done on a subset of trees because in 1977, they were really interested only in larger trees. And so there was kind of a subset of trees we were able to apply these results to. Here's some results that date all the way up to as recently as I think the most recent data point here is maybe 2 weeks ago. And so a student of mine, Arisa Quikus, is out measuring these forests as we speak. Well, not as we speak, but during the current time period is out there measuring. And then way back in the beginning, the project was joined by several former students that have now moved on to other professions. And so through time, this has really been maintained by students and faculty collaborating together. So every approximately 2 years, we go in and remeasure, sometimes longer, sometimes shorter. And as these bars increase, that is carbon that's accumulating in our system that we're able to measure through our plots. So through time, we've noticed a pretty steady increase with the exception of 1 year in there that we're kind of examining closely right now. We've had a pretty steady increase in carbon in our forests. And one of the nice results from that is that we were able to calculate the amount of carbon per year that our forests are taking up. And on average, this approximately equals the emissions from automobiles associated with the college. So the amount of automobiles that commute to the college, their emissions are essentially offset in a sense by our forest uptake, which is pretty interesting to think about, just one way to kind of put it in perspective. This is a large amount of tree biomass, and so it's also a really large pool. So we're approaching maximum carbon storage for a forest in our region. This is a trend that is common in forests of the Pacific Northwest. This is a figure evaluating carbon stores across the Pacific Northwest and thinking about how that change is expected to happen through time as a stand gets older, a stand of trees. And what you'll notice is a really steep increase in carbon in live tree biomass, that's the green. So trees increase in the amount of carbon they're storing on the landscape rapidly when they're young, and they'll kind of slow down a little bit as they get older. But of course, we're talking about when they're much older, 300 to 400 years, which not much of our landscape is in anymore. So most of our landscape is under 200-year-old trees, most of our forested landscape, and they're still in a heavy accretion phase. So they're still accumulating carbon relatively rapidly. This is a diagram that's been used in forest ecology classes by a professor, especially at the University of Washington, for a long time. And in my mind, it's relatively famous, though I'm sure a famous figure is not something that many people think about. But at any rate, this cartoon depiction of forest succession depicts some really important things. So this is a post-fire system where a fire comes through, removes some of the trees, kills some others, leaves them standing, makes room for young trees. And as forest succession proceeds, you get denser and denser forests, you get more and more mass of forests on the landscape. Remember, bigger trees, more mass, more carbon. And so we're kind of approaching maximum carbon as the forests age and go through succession. Now let's think about what happens as forests are progressing through time, because it really matters for our region and it matters for how we think about carbon, because there are some big questions that people normally have about how the carbon cycle works with regard to forest management. So here I have an image of a clear cut. And in this image of a clear cut, we can ask ourselves, what's missing? So, what do we have missing in a clear cut? And obviously the trees. But we've left a lot of other stuff behind. And so notice that there's a lot of small diameter material, small branches, treetops, leaves, small organic matter that's left behind. All that material is going to decompose relatively rapidly and will go straight to the atmosphere. There's also what we're not seeing below ground, which is the large root mass of these trees, which is below ground, now cut off from inputs from above that was sustaining those roots, and those are going to decompose too and go back to the atmosphere. So largely when we're talking about emissions associated with clear cuts or cutting of forests, that's what we're talking about. We're talking about the emissions of this material that's left over. As forests age through time, they become denser, and this is a typical planted forest plantation stand that will become so dense it'll start self-thinning. Eventually, the self-thinning of those trees due to light limitation will result in the stand opening back up. Here's an image from Evergreen in 2006, one of our stands that had been going through self-thinning and then is starting to open back up, and the remaining trees are larger. And then, of course, we can move into what we call an old growth phase, which is kind of our maximum carbon storage phase. And there's been some controversy about what old growth forests do in terms of carbon, where some people right now will say, well, old growth forests are still accreting and sequestering carbon quickly, and others will say carbon gain approximately equals carbon loss. And so it kind of depends on where you have been measuring. That'll determine your bias for an answer to that question. But there are examples of old growth forests that are still sequestering a lot of carbon, and there are examples of old growth forests that release about as much carbon as they take up, but they store a lot. There's not much to debate here. A lot of our old growth forest has been lost, and we don't have a lot of it left on the landscape. But we might start thinking about what it would look like to plan for redevelopment of those forests. Well, coming back to this issue of just forest carbon, let's look at a map again, and you're going to notice I'm going to do this a bunch. So here's a map of our forests based on remote sensing. And so this comes from a paper by Hansen et al., an approach by Hansen et al. And the images I'm going to show you now come from something called Google Earth Engine. And Google Earth Engine is a publicly available remote sensing and data platform. You could do this analysis I'm about to show you yourself by looking up Google Earth Engine and this example. So we're looking at images of forests here across our region. You'll recognize some of the topography. And then the next image I'm going to show you is going to be quite a bit different. So here we're looking at loss of forests since 2000, which is going to be striking to many of you if you've never seen this image before. So in our region, this represents where cuts have occurred in our forests since 2000. And I think if that doesn't strike a chord as being quite realistic to you, this might help. So here we have the same image, and this is an image where the loss is broken down to individual years since 2000. And so the different colors represent different years of loss. So it's not that all of that forest is lost at once, but every year there's a different amount of loss in a different location. And summatively, all the colored locations, yellow to red on this image, represent locations where forest loss has occurred through time. So that's just to kind of put in perspective our active and working forest landscape that is southwestern Washington. We have a lot of area of forest that's under direct forest management and clearing every year. I think it's useful to think of clearing of forests as really just another type of disturbance. So I want to talk about both clearing effects on carbon and fire and other disturbance effects on carbon. And so we're going to get to those. We're going to start getting to those now. Regardless of the way that a forest starts out when it's cleared, whether it's a clear cut or a fire or a windstorm, we think of that as kind of a low carbon scenario. And then we have these middle-aged forests, which vary in their structure. And then we get to our older forests, which tend to be more complex in their structure, and they also increase in their amount of carbon. These are images from Robert Van Pelt. So we go from low carbon storage scenarios to high carbon storage scenarios as forests age. And of course, once a forest is cut, there's a lot of that carbon that's lost back to the atmosphere. And so sometimes that's direct through the fires that you can see here in this image, where forest biomass is directly being converted back to CO2 through combustion. And sometimes it's more indirect, and it's a matter of the amount of decomposition that takes place after the disturbance has happened. If you've opened up the forest stand, you may have made a better decomposition environment, and the remaining material is going to decompose. Well, one question that I frequently get when I'm talking about forest carbon to students or the general public is, what about this issue of where the wood goes when you cut a forest? So if you think about cutting your forest and you think, well, I cut that forest, but I built a house out of it, doesn't that mean I sequestered the carbon? I think it's important to address this question directly. There are public questions that arise about this all the time. I think it's important to dispel that there's any debate about this in the scientific community. That hasn't, I don't know of a place where that's been a real subject of debate. And this is because it really boils down to some real fundamental principles that are just really easy to demonstrate for yourself. First of all, trees are not just 2x4s. And of course, this is one of these adages that, during the spotted owl debates of the late 80s and 90s, we'd say that a lot, but we'd say that a lot with the carbon, thinking about forest carbon too. It's important to remember they're not just 2x4s. There's a lot else there. And even if they were all 2x4s, what we make out of those forests doesn't necessarily last forever. And so wood products, not all wood products are forever. Now, some of them are, and some of them will stick around for a long time. But a lot of these trees that we're talking about in old growth forests, for example, have, 300, 400, 500-year lifespans. So much longer than the amount of time that most of our wood products are around, even the best made. And so the life cycle of that material plays into how we think about the carbon cycle on a broader landscape and a broader temporal scale. Of course, forests are not just trees. So trees are not just 2x4s, and forests aren't just trees. And so when we go in and we log a forest, of course, we're changing that system into something very different. And so we're leaving a lot behind. And a lot of the thinking about carbon balance is about what we leave behind. If what we leave behind is a dense forest with that carbon trapped in trees for 500 years, that's a lot different than leaving behind guaranteed decomposing material that's just been cut and left. And this is not to say, this is just to put carbon and forest harvesting in a realistic context. Like, these are just the realities that we have to deal with. And then we can move on from there and say, okay, we can decide how we're going to treat our forests, because of course, carbon is not everything too, right? There are other reasons that we do with forests. The effects of carbon storage associated with conversion of forests from a high storage system to a low storage system, like old growth to plantation, is something that's been addressed in the literature for a really long time. This is a paper by Mark Harmon et al. From 1990. This is a relatively famous paper in forest ecology circles, and not because it said anything that was counterintuitive to what people thought, but just because it laid out kind of the numbers and the models for what we should expect. So let's think about a forest through time, in this case up to about 450 years, and let's think about it in terms of the percentage of old growth storage. Now, we know old growth is that maximum carbon storage. So what happens when we disturb it? And we've got two lines on both of these graphs, and those would represent wildfire in the case of the solid line, or harvest in the case of the dotted line. And we can have some assumptions about that model, about how decay is going to change in those forests through time. And the details here aren't important, except to know that the cut or the wildfire occurs and we get a decline in carbon. We don't go to zero. We're not losing all of our carbon in either of those scenarios, but we're losing some of it, and then we're regaining. And we're regaining that carbon pretty steeply until we're going to reach some sort of plateau. in the amount of carbon we have. Now, if we think about carbon and forest harvesting in terms of these cycles, so you may be familiar with the idea of a forest rotation, or rotations in your entry into a forest to remove wood products. You know that a lot of our forests locally are managed on either every 40-year or every 80-year rotation. So every 40 or 80 years, you go in, and the idea is you go in and you log and bring that out and produce wood products. Well, the graph now represented here on the right is showing the percentage of old growth forest storage in a forest that's logged about every 40 years. And in multiple scenarios, with residues removed or wood stored in some cases, or residues left behind on the forest floor. And the main point of this figure is not the absolute location of these curves. The main point is that those curves don't get back up to 100%. So there's no way to cut yourself back into 100% of old growth storage. There is a way to grow a forest back into 100% of old growth storage, but you have to grow it back into something that resembles old growth forest. A lot of these emissions associated with forests post-harvesting can also be modeled remotely. So here again is an image from Harris et al. 2021 looking at these fluxes of carbon across the landscape. And we have sinks and sources of carbon, just like we did in the global map at the beginning of the talk. And now we have sinks and sources that are much more local. This is midway through Oregon here. And you can see a checkerboard pattern representing different land management and different patterns of either forest removal or forest growth. Around Olympia, we can actually do the same thing. So this is again using that platform I was talking about earlier from satellites. Clear cuts are really nice to see from satellites because they show up really clearly. They're really obvious. And so you can see them really clearly and tell when they were done and where they were done geographically. So this is a downstream analysis from that Harris et al. Work where we can look really closely in our own region and say, okay, how much of our region is forested, how much was cut in a given year, how much was gained in a given year. So we've been talking a lot about forest, loss of carbon following a cut, but of course forests regrow and they also pull carbon back in, and we have areas that were previously cut that are regrowing. So remember, it's the balance of both uptake and emissions that result in a change in how much carbon is on the landscape. And if you look at the amount that's cut or the amount of forest that we have on the landscape, it changes year to year, and it's not at all linear. We have these kind of ups and down cycles, and when our larger community composed of private landowners, state landowners, federal landowners, when they decide to do a management activity that results in loss of forest cover. Here's a graph that is just a result of summing these two things together and thinking about where do we have emissions from our forests. And so we could toggle back and forth between these, and you'd see pretty quickly that a lot of these pink areas representing tree cover loss are where we estimate that we have our highest emissions back up to the atmosphere. We can also think of this landscape in terms of locations where we could afforest or add forest where it isn't presently there. I think that this analysis, as done through this platform, you can see it's pretty, pixelated here. I'm not sure that the locations of those square dots are exactly perfect, but it's making the point that, we do have locations on our landscape. We could also think about moving more forest into and increasing our forest cover, increasing our carbon uptake. So in our evergreen work, we have gone through and used this forest as a model to both model the amount of carbon that we can measure directly on the ground and interface with some models based on forestry theory that show us where we expect them to be in terms of their carbon in the future. So let's start with the blue line and the yellow dot here. The yellow dot there is manual data in 2020. So we measured our forest plots at the Evergreen State College, and that's what we found our amount of carbon was. Where the lines start in the mid early 2000s, that is our initial data point that we started from, and we modeled from. So our model's based on those data. And you can see that the blue line, if we followed it across here, would be pretty close to what we actually measure in 2020. It's a little bit of an overestimation, but it's pretty close to what we know is there. So that's a good check on our model. Our model predicts then that, you know, somewhere around 2100, we would reach our kind of maximum carbon storage in these forests, and then we're going to grow at a pretty steady rate until then. The other color lines here show what would happen if we did a variety of different treatments, and these include just a cut and then a return after 80 years. They involve, what if we just went through and we thinned our forests, but we left all the big trees behind to grow old growth? Or what if we did kind of patch cuts, where we went through and we just selected small patches? What would our carbon be? And I just want to point out that regardless of those treatments, those would all have really different effects on our forests. They would have really different effects on what the forest looked like and what kind of animals it supported. But all of them result in an estimation of carbon that's far lower than where we would be without doing anything. Forests are just really good machines for taking up carbon. And so if we were only focused on carbon, which I would actually argue we shouldn't be, but if we were only focused on carbon, leaving them as they are is probably, you know, according to our models, our estimates, our theories, would be our best move. So some of you will initially react to that and think, well, what about fire? Doesn't fire destroy forests? Well, I've been thinking about fire and forests for a long time. As I said, a lot of my training in forestry is based out of the Intermountain West or the Southwest, where fires are common. They've made a lot of headlines this spring. They can be dramatic. And there's been active forest restoration and fire reintroduction in those forests for a long time. But there ain't here. And so that's a really important concept when we're thinking about what to do with our forests and how fire interacts with our forests. What I see time and time again in forest ecology is that people tend to take results from a bioregion that's very different than where you are, and they try to apply lessons to their current bioregion. So there are really different fire regimes, different types of fire, different frequency, how often it comes through, and different vegetation dynamics in Southern Oregon, in the East Cascades, or in Thurston County. And there's also a lot of variation on the landscape, but it's really important to keep that in mind. Every forest is different, and every forest fire regime is just a little different. So when we think about East Side Ponderosa Pine Forest, where a lot of our news about fire reintroductions and wildfires comes from, these forests tend to be forests that are adapted to low intensity, high frequency fires. They come through very frequently in time, but each time it's kind of a light burn, and the trees are adapted to withstand that. The older ponderosa pine trees may be adapted to withstand. And these are forests, people talk a lot about going in and cutting out forests that are too thick and thinning those forests so that they can reintroduce those fires. That's a really different scenario than the photo on the bottom right, which comes from Ellsworth Creek near Willapa Bay. We have many forests in our region that look more like this. We have continuous, what we'd call fuel ladders from the ground into the canopy. We have dense vegetation and dead woody material on the ground. This is natural. This is not an unnatural, human-made forest condition. This is how these forests grow, and they have a really different fire history and a really different history with how they interface with carbon as a result. When these forests, like the ones in our region, go off, it can be really dramatic, and so it's easy to jump to dramatic statements about what's happening. This is an image from the Holiday Farm fire in Oregon, a devastating fire just a couple years ago now along the Mackenzie River. Here's an image from the Columbia River fire, the Eagle Creek fire that was several years ago now. This fire threw firebrands across the Columbia River to the Washington side. So that's how intense that fire was, and that's how far it was able to attempt to spread itself. And once these fires burn through our dense forests here in the Pacific Northwest, the results are not always totally intuitive. So a lot of times you'll hear, well, if that fire comes through, we are going to lose all of our carbon. And think closely about an image like this. So here's an image looking at a forest that burned near Mount Adams. Of course, our forest is gone, and in many ways, we've lost our live trees. But if you ask yourself, is there any carbon left in this forest? As a carbon scientist, undeniably, yes, there's a lot of carbon. And in fact, there's a lot of carbon in the parts of the forest that don't decompose very fast. That is the large tree boles. So there's a lot of carbon left here. The forest has been killed, but the carbon stores are actually still quite high. Here's an image from, again, the Oregon fires. This is the Columbia River Gorge fire after Eagle Creek. And this is a spot where the fire came through. It looked really devastating. And then now we're seeing some kind of regrowth of the understory vegetation. And again, a lot of carbon storage still there. Here's another image from the Eagle Creek fire. You can see off of I-84, one tree has been felled in the foreground here. We have a number of dead trees. And as you look at images of this fire, you can find many images of many, many dead trees. But what you'll also see is a lot of carbon still on the landscape. So if we think about loss of potential carbon storage in all of our forests, we can think about that in terms of loss due to harvest, loss due to fire, loss due to something like insect damages, or all disturbances together, right? And so here is a graph for the Gifford-Pinchot National Forest from about 21 years, from 1990 to 2011. And you'll see that harvest is the biggest impact and loss of potential carbon storage, though it's not a huge loss, but it is some loss. And again, national forest, so there isn't a lot of harvest happening there right now. Here is a similar graph from the Willamette National Forest, and note where the fire only line is, and I'll toggle back and forth here. So our fire only line is up near our blue line there. Very little loss of potential carbon storage in the Gifford-Pinchot in those 21 years. And you go south to the Willamette National Forest, and you have tremendous losses due to fire only. So different fire regime, different losses, right? And in that system, the losses due to fire may equal the losses due to harvesting, which are also larger than where we are. So different forest conditions, different fire regime, different impact of something like fire. Here in our region, we have a history of many locations, this is on the Olympic Peninsula, that have actually had fires in recent years, sometimes in really dry portions of the year, that haven't resulted in the same kind of widespread fires. It doesn't mean they couldn't in the future, but they haven't necessarily. So if you look in this image, you see a lot of burnt trees. You see some trees that have been killed due to fire, but you see a lot of carbon on the landscape. Here's an image from the Evergreen State College. We had our own accidental fire. It wasn't associated with anything that the college was doing, but we had somebody who decided to, from outside the community, come and camp, and a fire got out of control. Where they were, it was quickly put out thanks to DNR, and it was just a small footprint. But it enabled us the opportunity to kind of see how a small scale fire would interact with our forests here. And you'd hardly know from this photo alone that this is an area that burned in 2018, and this photo is a year old now. So this is a system that was able to deal with kind of a small scale fire. This was in September. It was a time when you'd expect fire to rage wildly. It didn't. And we were lucky for that. So fire doesn't always have that kind of immediate devastating impact. Of course, logging is going to have an immediate impact. This is a small scale ecological forestry treatment, small scale gaps where trees have been removed because they were likely to succumb to something called root rot outside Capitol Forest. And you might ask yourself, what is a more fire dangerous scenario, a forest like this or a clear cut? And that's an open question for debate we've got to think about in our region. And of course, our landscape is made up of a real mosaic of forests that have been treated in wildly different ways, sometimes leaving behind a lot of dry material, sometimes maintained in kind of moist forest conditions, and sometimes in intermediate growth conditions. And so we're still waiting on the answers of how a lot of that will interact with something like fire, but what we do know a lot about the carbon storage trajectory for those landscapes, both with and without fire. Okay, just returning to that graph there. and highlighting that I was able to show what would happen with cuts, modeling that, but what would happen with fire, it's unknown, but it's probably intermediate between what the cuts would do and what a do-nothing approach would do. Well, I just want to leave you with 4 kind of principles for preserving carbon. So if you're thinking about carbon on the landscape, what are 4 principles that would leave the landscape in the highest carbon density? So 1, I think if this was your goal and this is what you wanted your forest to be, first off, you have to recognize that carbon stored is better than guaranteed loss. So you might worry about the risk of carbon being lost due to a pathogen or a fire, but you can guarantee its loss when you disturb a forest intentionally. So you got to be aware that having it stored is probably better than guaranteed loss, especially over the landscape. Land in forest preserves carbon, but land and forest, even if it's cut and even if it's burned, preserves carbon on our landscape. So it's something I didn't touch on a lot in this presentation, but having so much of our landscape in forests rather than, for example, in development, keeps our forests in carbon. And so even if they're cut or burned, none of that compares to what happens if we completely take our landscape out of forest conditions. Next, though, one approach really doesn't fit all when it comes to forests and thinking about things like fire. So we have to be really careful of these anecdotes we hear. One time, I had a neighbor in Colorado, this happened to their forest, and therefore we should do this in my Puget Sound forest near Olympia. That's a really dangerous transfer of information, and we got to be really aware of what we're doing when we're doing that. We're making a lot of assumptions about how our forests work and how disturbances work. And along with that, learning from our local systems is probably the most important thing we can do. Every forest is a little different. They've got a little different personality, moisture regime, species. All of you know this if you have a forest that you've spent time in. They all have these unique characters. And understanding that character is really the key to understanding how to interact with that forest to maximize that forest growth and its carbon storage. So learn from local examples, learn from your local forests, learn from natural history. Okay, with that, that's really just about what I have. I just want to leave you with one kind of ray of hope from our neighbor on the other side of the globe. This is an article from a couple weeks ago now on Tasmania and how Tasmanian forest practices have changed, especially since 2011, where they've really focused on what they call responsible forest management, but it's a forest management approach that's resulted in higher carbon storage in their forests, in their temperate rainforests. And as a result of that, Tasmania is now carbon negative. That is, it's a location that is taking up more carbon than it's releasing, much like Thurston County could be doing. We're already doing that with regard to just our forest emissions. We could be doing that with more probably if we worked at it. But anyway, just kind of an interesting idea. Let's leave that there. And if anybody has any questions, I'm happy to stick around and answer them. Thanks, everyone.
Ellen.
Yeah.
I didn't see any questions in the chat line. Anybody put questions in the chat line, or just go ahead and turn off your mic and ask Dylan directly?
Thanks, Gary. Thanks, Maureen. And anybody should feel free to contact me too. I love, obviously, I kind of love talking about this stuff. So I'm sure some of that talk is going to leave you with more questions than answers. And so, yeah.
And we recorded this, so we'll put it on our Stream Team website.
Great.
So then folks can go back to it and listen.
Okay.
A lot of information.
Yeah.
Here's one. What's the future DNR legacy forest in the South Sound?
That's a really interesting topic. It's a little, unfortunately, a little outside my wheelhouse. About my understanding is we've really just, in the last year especially, we've really enhanced our protection of our legacy forests. So legacy forests, for those who don't know, are these forests that they're not quite old growth, but they're older than a regular rotation. They're often dating back into the 1800s, and they're approaching old growth status. Oh, does every tree species net the same amount of carbon by weight? And no, that's a really interesting question. So trees vary in their density of wood, especially, and so they can really differ in how much carbon they have by weight. You can think of a balsa wood, for example, versus a really dense ironwood or even a cedar, and so they can be pretty different in the amount of carbon they have. Should I keep my 100-year-old wooden house? Yes, please. That sounds, yeah. My house is 100 years old too. Congratulations to your house. Certainly from a carbon perspective, we would lose some of that carbon to the atmosphere if you demolished it.
Michelle, there is a question in the Q&A.
Yeah, I was just looking at that.
Okay.
How can we protect our homes and areas from forest fire?
This is a really great question for our time. And I think we have to realize a couple things. One, that we're in an age of, information transfer from other regions about things like wildfires is faster, more frequent, more in our face. And so it's really, and then the smoke that we've all been experiencing in the summers puts us really close to thinking about wildfires in our area. And there's no real easy answer in our neck of the woods for this. And one thing that I think we can almost guarantee is that the approaches that people advocate in the Intermountain West are not going to be the same for us. For example, this idea that you can just keep around your home, make sure that around your home is clear of vegetation and nearby forests. And I'll give you an example of why. That Columbia River, the Eagle Creek fire that I showed you images of, that's a fire that threw firebrands over a mile away. So these mega fires that can occur in our region operate at a scale that is just really different than any fires that you hear about, unfortunately. The Beachy Creek fire and the Holiday Farm fire in Oregon a couple of years ago, those fires burned equally through clear cuts and intact forest. And so it's not a matter of clearing vegetation. It is a matter of monitoring fires in our location, keeping aware, keeping informed, having clear routes for exit like you would with a tsunami, and being aware of where to go in the horrible case that we have to deal with that. If you think of that Gifford-Pinchot figure that I showed you, our region we're not experiencing the same fires yet like they are in Oregon and a lot of places in California. It doesn't mean we won't in the future, but yeah, big topic. So thanks for bringing it up.
Another question, do we have stats on how much of our green in the West are tree farms and how much is older?
Yes, that's relatively easy to pull together. I don't have the stats at the top of my head, but we could divide the landscape into industrial forest lands and non-industrial forest lands. What's hard to get a handle on is the individual private small family farms, which can be more than half of our forests. In Thurston County, they're more than half of our forests. They're a large proportion of forests in Western Washington. And sometimes those family tree farms can be treated like plantations, and sometimes, as many of you know, they're not treated like plantations at all. They're interacted with as forests. And so that's a harder thing to get a handle on except through satellite analysis.
A question about what kind of trees to plant. We always recommend native trees, but also plants have varying different needs, soil.
Yeah. Yeah,
That's
yeah, and if you were just interested in carbon storage alone, and again, I wouldn't advocate that's the sole. I don't think we should ever manage a landscape, with just a singular goal in mind. But if you were interested in that, you might start concentrating on planting, redwoods and giant sequoias, maybe. I mean, so there are ways that you could plant trees that would accumulate more carbon even than a species that we have here, but they wouldn't be native. And so what is happening on a more realistic scale in our region is we have more people that are trying to do some assisted migration by moving seed sources, for example, of something like Douglas fir, and planting Oregon seed sources of Douglas fir near Olympia, for example. So thinking about that kind of assisted migration and moving that genetic stock north. And the jury's still out on whether that's a great idea or a gamble. Other people go further, and locally we have family forest farms that are planting ponderosa pine, that are planting much drier species that have some local. There are native ponderosa pine in our region outside of Olympia, and so they can plant those. So I think that that's a hard question to answer without seeing a plot of land. But I think Douglas fir, cedars, these are great trees still for our region to plant.
Let's see, a couple of.
Here's one about soil from Joseph McGee. Carbon in soil, I didn't show the figures on that, but if we think about the total carbon storage in a forest ecosystem, not just the trees, not just the vegetation, if we look at the total amount of carbon, half of that would be in the soil, at least. And so it's a huge carbon store. It's not, the reason we don't talk about it as much in the context of what I was presenting on today is that it's not as dynamic of a store. And so what that means is that it doesn't decrease as fast and it doesn't increase as fast in forest soils. And so it's harder to get forests to increase their soil carbon stocks in a measurable way than it is to have them increase their above ground tree carbon stocks, which are visible and very obvious. But they are really important. And any carbon scientist would tell you that, and would be measured in a long-term project. A lot of these, the thing about an intact forest is it's really good at getting carbon into the soil too. Eventually, it's just a longer time scale. Here's one about net emission, net storage, and carbon balances related to harvest. How do alternative building materials fit into the equation? Do harvests replace more emission intensive materials? And that's a really interesting question, and it would really depend on what those alternative building materials are. And what the life cycle analysis of each of those materials is like. How long does it last? What's the embodied energy that it takes to produce that material, in addition to how much actual tree carbon goes into that alternative building material? But Kellyanne, that's a great question. Looks like JJ, Jay has a raised hand.
Okay, there we go.
Yeah, you should be able to talk.
Can you hear me?
Yep.
Okay.
Yeah.
A couple questions. One on that last question about the soils storage.
Mm-hmm.
Are we talking about the soil storing so much in a forest landscape because of the roots? Or if we take out that forest and we also, I don't know how much of the uprooting they do when they come through those forests. I assume they take the roots because they have to replant. Is that what's storing most of the carbon in the soil or not?
The roots are interesting. I mean, and thank you. It's one of my specialty areas. Roots are really interesting because they do contain a lot of carbon, but often not as much as we think. And so, they may represent something like 20% of the total tree carbon stores. And that's a significant amount. That's a big amount of carbon. But that's not all the carbon in the soil. A lot of the carbon in the soil is going to be humic material. It's that kind of, it's the stuff that makes your garden really great, you know? And when you've got a really nice soil in your garden, it's full of all this kind of dark, rich, organic material. And a lot of our forest carbon is in that material. It can also be in the leaves and dead litter at the very top, which is a little bit more dynamic. But that humic kind of rich, you know, fertile soil stuff, that's the stuff that doesn't change in its content very fast, although it does change. And it is really important to preserve. Keeping forest in forest preserves that. And generally after we cut it, because we change the amount of rainfall that a soil receives and the temperature gets more direct sunlight, then that material is respired off by microorganisms faster. And when it's respired off, it's going back to the atmosphere. We also have some carbon in rock. And so we can also have and so as we go deeper and deeper in the soil profile, we have other much less dynamic stores of carbon that don't change very fast at all and won't be affected very quickly by forest management.
Can you still hear me?
Yes.
Yeah. So when you take that tree layer off and you now have affected the way that the soil is going to store the carbon, do we have any sense about how much is lost through respiration? And I mean, is it another 30, 50% that we lose, or do we have any sense of that?
Yeah, that's a good, I think the estimate around 30, 50% is what I would have to, that would be my ballpark estimate for what we'd lose, assuming in our region that we have a forest that then is going to regrow again and relatively quickly. So, but that's going to change depending on, you know, slopes, underlying geology, lots of kind of site specific factors. So we can lose a significant amount due to respiration just from cutting. Assuming it's going to grow back, we can recover that, but it takes a lot of time.
Right. And my second question was about fire. And I'm really curious about this. There's a lot of argument, obviously, about how the fires move, hottest,
Yeah.
whether it's in established old forests or whether, whether selective harvest, et cetera, decreases that, et cetera. Mm-hmm. You might have addressed this sort of when you answered this other question, but maybe if you can just go a little deeper into that and what we know about which kinds of forests really discourage that kind of fire, that kind of really, they're really destructive fire.
Yeah. So the really destructive fire that's a hard thing to, okay, so let me back up a little bit. So when we think about the really destructive fire, we can have a really simple model where we have the really destructive fire on one end and we have the really light friendly fire on the other end. And what we're usually thinking about in those scenarios are two really different types of forest. So for example, the ponderosa pine forest that I showed you, where the trees are lightly spaced and fire is just kind of moving through the landscape and with a really low intensity, really low impact on forest carbon stores. We're losing some, but not a lot. And then at the other end of the spectrum, we can think of a number of different scenarios where we get a catastrophic wildfire or a crown fire. Now, sometimes that can mean we have a ponderosa pine or an arid land forest that's been mistreated, or fire's been excluded from that zone for too long. And that's a story, probably a lot of people have heard by now in the news, where fire exclusion has led to a buildup of trees and then dangerous situations. Okay, so that's one place where we can get destructive wildfire. Wildfires like we've seen recently that are big in the Pacific Northwest, like those fires in Oregon a couple years ago, or the Columbia Gorge, the Eagle Creek fire, for example. A lot of those fires are what we call climate-driven fires. And so they're not as dependent on the nature of the forest conditions. They're more dependent on the nature of the climate. And so we get these really dry east winds that come in, and then we have an ignition source, really heavy, dry winds and warm conditions in a season when everything is dry already. And in those scenarios, it's really hard to think of a forest structure that's fire resistant. And so this has led some folks, including Jerry Franklin, a relatively famous forest scientist in our region, to really advocate that on the west side of the Cascades, we should think about things like forest suppression. And so, fire suppression, sorry. So fire suppression, and the idea being that, if we let fires go, then they can get catastrophic like that. I'm not so convinced of that because I've seen so many examples, especially recently in the last 10 years, of fires that have happened even in dry, relatively widely spaced forests that almost look like ponderosa pine forests on the Olympic Peninsula, for example, where we have steep habitat, where we have fires that have come through and they haven't been as devastating as what we've seen in other places. And we have a lot of tree survival. And so I think we have a lot to learn locally. This isn't going to be a great answer to your question because I think that we're still at the beginning of understanding what our new kind of climate regime and forest structure looks like. Now, we know what we could do to forests to make them so that fire couldn't really burn through them very, very much. But they wouldn't look like forests anymore. They'd look like golf courses. So, if we still want forests in our region, we're probably not going to thin our way out of the fire risk. For one, the thinning is going to open up more sunlight into those stands, and it's going to dry out a lot of the fuels that maintain moisture. That stump in your favorite forest that still seems kind of moist in the middle of summer, that's a fire preventative structure, right? That's slowing down fire when it comes through your system, not speeding it up. The pile of dead, dry, small diameter sticks that look just like you'd stack kindling that are in a clear cut, that's going to expand fire. And so these things, there's a lot of complexity. I hope that got at your question. I know it wasn't a clean answer.
No, it's a good answer. It's just that I guess what I'm hearing at the end of that, though, is that what you're really saying is that the deeper, denser forests really are a kind of fire break. So to me, it sounds like you're saying that, like when that sunlight's not getting through, when we haven't gotten those dried out forests, when we have the big, quite moist forests that we're talking about west of the Cascades, then it sounds like we're really saying that we really need to preserve those and suppress fire, if I'm hearing that sort of right.
I think that those are likely linked. And of course, I have to rely on kind of anecdote and my experience with this because I don't think our studies are done for this. And it'll be really interesting to look back at these Oregon fires and see if in fact there was any kind of fire resistance that was embedded in those kind of wetter forest systems. But that's my sense for our region. Yeah. That would be my final answer. That I think that those denser, wetter forests, not only are they good for carbon storage, they likely are actually a fuel break.
Thank you.
Yeah.
I also put in the chat. I put in the chat. We had a lecture, Josh, with DNR on Western Washington wildfires. It's in our reference page, and I also put the YouTube link in the chat line.
Yes, and Josh was terrific.
Yeah.
Done some great work on this.
All right, thanks. Thanks, Dylan, for coming tonight, and thanks everybody for attending. Yeah, thanks to everybody. And Joseph, I see we didn't get to your question about Western red cedar dieback. There is a great Washington State Extension Office page on Western red cedar dieback. Just email me if you want a link to that. I'll try to connect you. Thanks, everybody. I really appreciate it. It was really fun to talk and great questions.